Hello Chem 1A, this is Chapter 8, Lecture Video 1, and we're going to be talking about the structure of atoms. This chapter is going to be part of our Exam 3's material, and just to kind of give you some idea here, we'll learn more about why these jokes are jokes, I guess, if you can call them jokes, later in this chapter. Primarily, it's based off what the physicist pretty much renowned for the creation of quantum mechanics, Erwin Schrödinger. And when he first kind of described it, one of the ways he describes it is by the cat in the box example. And it's a little bit not great for animals, but he said that an electron is like if I put a cat in a box with a bottle of poison and close the box. I do not know whether the cat is dead or alive until I open the box. In other words, I observe it. But this is all his analogy. I don't really like the dead cat part, but he posited that because he doesn't know until he measures it, the cat is currently in a superposition where basically it's both dead and alive at the same time. This is related to electrons, where we actually don't know where an electron is or how much energy it has until we actually measure it. And when we measure it, it's different due to the measurement. So it's a relation to that, and we'll talk a little bit more about the uncertainty principle and Schrodinger's wave functions. But that's what these two are relating to as far as the joke goes, is that the cat survived, haha, and then you're doing something and nothing at the same time. Basically, you're existing and dying at the same time is the joke. Anyways, moving on. Before we can really talk about quantum mechanics, we got to talk about electromagnetic radiation. And electromagnetic radiation is light. Now, we need to talk about some of the properties of light. It has both the characteristics of a particle and a wave. Now we'll talk about the particle side on the next slide. Let's talk about the wave. All waves, when moving through space, kind of have a trough and a peak. Up and down is what they do, right? So in this picture here, you can kind of see it goes up and down, basically continuously until it hits something, basically. Now, because of this, there's some properties of light that we need to talk about due to its wave. One of them is the wavelength. So if we look at this picture, we have this bar here, that this is our wavelength. Now the wavelength is a distance between peaks or troughs in our wave, right? So we could have also drawn equivalent lines down here. And you might notice that they're the same length or very close to that, regardless of which one I drew from. Very top of the wave to the next top of the wave, that would be the distance known as the wavelength. Or from the bottommost point to the next bottommost point would also be the wavelength. Now, how light travels through space is based on this equation, which is c is equal to, this is actually a Greek letter nu, but we can think of it as a v, and this is lambda, and lambda is actually the symbol for, as you can kind of see over here, wavelength. Now, nu, or the little v, is actually the frequency, and so that's the other property we do need to talk about. So c is the speed of light, and it's a constant in a vacuum, and we're just going to assume we're always in a vacuum for this chapter. If you want it out to 3 decimal places, it's 2.998 times 10 to the 8 meters per second. Usually we just say 3.00 times 10 to the 8 meters per second. Now, wavelength is, like I said earlier, the distance between two peaks in the wave, and we typically measure this in a distance unit, nanometers. Now, why nanometers? Because most visible light has wavelengths in about 350-ish to 800 nanometers of wavelength. That's visible light. And so we typically use nanometers as our unit for wavelength. Frequency is a little bit harder to define, so I'm going to try using some waves here. If we look at a wave that I'm doing in yellow there versus the wave in green here, Frequency is defined as the number of occurrences of a wavelength per unit of time. So let's think about if I have time starting here, and this moves at the same rate of speed until we get to here. Which one of these had more wavelengths occur? Well, hopefully we can clearly see it's the bottom one. This means that the frequency for the bottom one is going to be much higher than the frequency for the top wave because more wavelengths went through, right? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost 11. 1, 2, 3, 4. Obviously, we got through a lot more occurrences of the wave in the bottom versus the top. This means the frequency would be much larger for the bottom wave that I drew. Now, we typically measure frequency in hertz or inverse seconds. These two units are actually numerically equivalent to each other. Cool. So there's actually many different types of light out there. And we kind of need to have a good feel for it. So light is made up of particles as well. Like I said, there's kind of a wave-particle duality with light, and the particle that light is made up of, or electromagnetic radiation, is a photon, not to be confused with proton. Protons, those are subatomic particles in an atom. Photons are the particles that make up light. Now, the reason why light has this wave-particle duality is light has energy, which typically we think of only as being reserved for particles. Particles moving through space have energy. But that's part of it. There's more to it than that. That's a really simplified definition of it. But because light has energy, the energy of a photon is actually dependent on either the wavelength or the frequency. They both matter, and they're both related to each other. Now, if you look at my little spectrum here at the bottom, you can see that as energy, ooh, that's a bad color, as energy increases going this direction, what is happening to our frequency and our wavelength. So frequencies here, wavelengths here. As you can see here in the radio waves section, we have really large wavelengths. But up here in our radio waves area, we have really low frequencies. And then as energy increases, frequency also increases. But as energy increases, wavelength decreases. And you should know this relationship that as energy increases, the frequency increases, and as energy increases, the wavelength decreases. You should also have a general gist for the order of energy of the spectrum, right? So I should know that basically gamma rays are the highest energy type of light. You should know each type of light. So we have gamma, X-ray, UV. This tiny little section here is our visible spectrum. This is what our eyes can see. And then we have IR, we have microwave, we have radio waves, we have long radio waves, and they kind of follow this energy pattern. There is actually another group over here called cosmic rays. I don't really need you to know about them, but they're kind of cool. They're the ones out in space, and they're part of the reason why a trip to Mars for a human being is unlikely in the near future, at least, because the amount of radiation you'd be exposing yourself to from cosmic rays is deadly. So you'd pretty much die before you got to Mars, at least currently, until we can figure out a way to protect ourselves from these really high energy forms of light that are only out in outer space for the most part. Kind of neat. Anyways, so I need you to know that gamma are higher energy than X-ray, UV is lower than X-ray, then we have visible light, then we have IR, microwave, radio waves, long radio waves, and you should kind of have a feel for how we move through this spectrum here as well, right? So red light is our lowest energy, and then as we go from red to purple, we see an increase in energy throughout the rainbow. All right, cool. So let's continue on.